Hello, and welcome to my presentation called Hazard-Specific Thunderstorm Nowcasting using machine learning with satellite, radar, and NWP data. In this talk, I'm going to describe our nowcasting efforts using machine learning and how we are able to identify the value of different data sources in the data. This project is funded as a EUMETSAT fellowship, which started in October 2020 at MeteoSwiss. The main objectives of the fellowships are first to evaluate the benefits of the Meteosat third generation or MTG satellites for thunderstorm nowcasting, and second, to work with the use of advanced machine learning, so for example convolutional neural networks with Meteosat second generation or MSG and MTG-like data, and third, to develop hazard-specific nowcasts for different hazards for the needs of the specific clients. We have heritage in this project from previous nowcasting projects as MeteoSwiss. So for example, the coalition series of algorithms, as well as the TRT algorithm. We are in collaboration with Hewlett-Packard with regard to supercomputing, with the University of Bern, with regard to their expertise in hail, and with the University of Alabama, who are experts on thunderstorms, especially in the United States. And we also stay in communication with a similar fellowship in Vienna. Thunderstorm hazards are highly localized and they develop quickly. And for this reason, it's hard to predict the time and the location where they happen exactly using numerical weather prediction. So weather forecasts might give you an idea of where generally there might be thunderstorms, but it's difficult to say where exactly they will strike on the short term. And for this reason, for the short-term prediction, we usually use what we call nowcasting, which is statistical prediction from the latest measurement data. And we can also talk about seamless nowcasting, which is combining nowcasting with the numerical weather prediction forecast. And since this is a statistical technique, machine learning has a lot of potential for nowcasting. But a problem is that there is lots of data available, but we're not always sure which data sources we should use. And specifically, we're interested in this project in what kind of benefits we will get from the Meteosat third generation for thunderstorm nowcasting. In the first project of the fellowship, we are trying to evaluate the contributions of various data sources to thunderstorm nowcasting. So for example, we want to evaluate whether radar data or satellite data will benefit the nowcasting of specific hazards. We then want to provide guidelines for data source selection in later studies, whether there might be ours or somebody else's. And we want to nowcast concrete hazards, so for example, lightning or heavy precipitation. And we are trying to use the same machine learning methodology for all of the hazards we evaluate so that we can compare better between the different hazards. As I mentioned earlier, in this project, we want to evaluate the benefits of MTG to thunderstorm nowcasting. And compared to the MSG, MTG has a higher resolution imager as well as a lightning imager. MTG is not yet flying, and this is why we performed this study in the United States, where similar instruments are already operational in the NOAA GOES-R series satellites. In total, we use 5 different data sources in this study. So we have the GOES-ABI and GLM. We also get the radar data from the ground-based NextRed network, which is operational in the United States. You can see the locations of the radars in the orange circles here. We are using also ECMW forecasts and the digital elevation model called ASTER. We gathered data from the study area in the northeastern US for April to September of 2020. and we co-located everything to a single grid so we can handle the data in a similar way for all data sources. So our overall strategy is to first identify storms in the radar data and extract tracks from that, then to compute features along these storm tracks, create training, validation, and testing datasets for the machine learning models, and then train these machine learning models for different hazards. And finally, to evaluate the importance of the different data sources using this machine learning framework. We identify the storm tracks based on a radar reflectivity threshold from the NextRad data. And we compute the tracks of the storms using optical flow with a software library called PySteps. And once we have those tracks extracted, then we compute features from the neighborhood of these storm centers. So we take the value of the different variables in the neighborhood of the storm center, and then we take features like the mean or standard deviation of the neighborhood. And when we combine the different data sources, different variables, different feature types, and also different time steps, we end up with about 4,000 different features and about 80,000 training samples. So once we have all our features collected, we train our machine learning models. And we do this using an algorithm called gradient boosted trees, which basically grows a series of regularized decision tree models in a way that each successive tree corrects the error of the previous models. So you start with one relatively weak predictor, and then you train subsequent predictors to correct the error of the previous ones. We implement gradient boosting using a library called LightGBM. This is a library that has turned out to be highly performant. It's also fast to train, even if you have many inputs, like is the case in our study. And it can also easily compute the feature importance. We consider 3 different thunderstorm hazards. First, heavy precipitation, which can be indicated by the radar reflectivity. Second, lightning, which we get from GLM. And third, hail, which is related to the presence and the height of a 45 dBz echo in the radar data. So let's look first at the results on the radar reflectivity. It turns out that predicting the reflectivity is rather difficult. On the graph on the right here, you can see the orange line, which is showing the persistence assumption, which is basically just assuming that the reflectivity will stay the same as it was at the reference time. But we noticed that this persistence assumption is biased. That is, the radar reflectivity more often decreases than it increases. And if we just correct for this bias, we already improve the accuracy of our prediction quite a lot. And then it seems that with the machine learning, we don't actually improve upon this bias-corrected persistence assumption that much. So this seems to be a pretty difficult problem. But more encouragingly, we get a little bit better results for predicting lightning occurrence, as well as the 45 dBz ecotop occurrence, which get 86 and 87% accuracy. Now let's look at the feature importance. So first here on the left, we have the feature importances for the lightning occurrence. And for that, it's not very surprising that the importance of the features from GLM, the lightning mapper, is the most important. So this basically just means that a thunderstorm that is already producing lightning is likely to continue producing lightning also in the future. But we also see in these blue bars here, for example, that we get more information also from the radar data, or the green bars here show that there is some contribution from the ABI satellite bands. And then if we look at the plot in the middle, we see the prediction of the maximum reflectivity, which is related to the precipitation. And since this is defined by the radar, it's again not so surprising that the radar is the most important predictor here, although we see that the algorithm also considers the NWB features quite important, as well as some of the satellite bands. And then on the right, we have the presence of the echo top. And again, this is a radar-defined variable. And here, even more than in the case of the reflectivity, this is dominated by the radar-derived features. Another, perhaps more comprehensive way to look at the importance of the data sources is to use different combinations of the data sources and then retrain the machine learning algorithm for each combination. So this example we have here shows the error on lightning prediction. And the way you can read these charts is by combining the row and the column. So for example, the top row and the leftmost column correspond to using all the data sources, while the bottom left corresponds to having just the ABI and the NextRad. And then you can kind of see on the color of the heat map how the presence of the different data sources affects the performance of the machine learning algorithm. So then looking at the importance of the different data sources in this way, we see first on the left for the lightning occurrence that these rows here that are darker color, which means better error scores, fewer errors, they correspond to the ones which have the GLM data available. Again, not very surprising, but it can also tell us that, for example, the ABI gives us some benefits in predicting the lightning. Or in the center column here, we have the importance of the different sources for predicting the reflectivity. And here we see in the two leftmost columns the cases where the NextRad data are available. And there we can also see this effect that the cases where the NextRad data is available are giving better results than the ones where we don't have them. And then on the right, we see the prediction of the 45 dBc echo top presence in the radar. And again, here is the same effect that the cases where the radar data is available have better results, but here the effect is much stronger still than in the prediction of the reflectivity, and the other data sources are less significant here, although they still give us a much better result than having nothing. So that was an overview of the results. And for a summary, we have the results of this first study, whose results I just presented, submitted as a paper. It's in review. We have the comments and we are answering to them right now. This is available in the address here. And then further in this project, this is a 3-year fellowship and we are about 1 year into it now. So further ahead, we are going to look at using the convolutional and recurrent neural networks using a grid-based approach. So not identifying storm objects, but rather running the prediction directly on a pixel-based grid. And we tested networks for this application recently in the weather forecast competition, which was run using the Nowcasting SAF data. Showing a quick example of the predictions of this here below. And another thing that we're going to be doing in the future is to develop this application for operational use in Switzerland and also in Europe and possibly in other areas as well. So thank you for listening to my talk and have a good day.